All right, let's do some examples. So this first example, we have a car traveling along a road with a speed of v is equal to 2s meters per second, and s is in meters. If the corner radius, or the corner has a radius of 50 meters, find the magnitude of the car's acceleration when it has traveled 10 meters. So if we need to find the magnitude of acceleration, so what we're looking for is the magnitude of the acceleration. That should tell us that we want to look for the two components of acceleration. So we want to try and find AT and AN. If we want to find AT, we need to find the time derivative of our velocity. And if we want to find AN, we need to find our velocity squared, our speed squared, divided by our radius of curvature at the point that we care. So this is when S equals 10 meters. So where should we go? I'll save a little bit. Where should we begin?
Could you solve AN and use your V equation and sub in 10 for S?
Yeah. So if we know our normal component is going to be and V is equal to, where is our equation? 2S. So when it's 10 meters, this is going to be 2 times 10 meters, so 20 meters per second. Right, that would be our speed. So we can write AN is equal to 20 squared over our radius of curvature, which is 50, which is equal to 8 meters per second squared. So we have 1. What about our tangential component?
Can we use the formula A ds is equal to V dV and then rearrange it to get V times dV over ds, and then that gives us our acceleration tangential, and then plug in 10?
Yeah. So our acceleration, our tangential component, AT, was equal to V dot, right? So we can write V dot times ds is equal to V dV. Right? So we have this equation. Where will we go from here?
V dot is then equal to V times dV by ds.
All right. So we have an equation for V. We know that function for V is a function of S. So we can calculate dV ds. And we'll end up with V, which is equal to 2S times the derivative dV ds, which is just equal to 2. So we end up with our equation for V dot is equal to 4S. And if our distance S is 10 meters when we want to do this analysis, so we can say at S equals to 10 meters, our v dot is equal to 40 meters per second. Oops, v dot. And that is our tangential acceleration. So our last step, we're asked to find the magnitude of the acceleration. We just need to take the square root. So the magnitude of acceleration is equal to the square root an squared plus at squared. So our an was 8, and our tangential was 40. And we should
Can I
get
ask a question?
Yeah.
Why can't we, since at is equal to v dot, why don't we do like the derivative of 2s is at? Why doesn't that work?
The derivative of 2s. So
Because wouldn't that be v dot?
let me write. Your v dot is equal to derivative dv dt, right? So you're asking, why don't we just do this?
Yes, I think you just answered my question though, because it's over dt. Yeah.
Right. So yeah, whenever you see the dot, think it's a time derivative. So if we don't have a function of our path or the function we want to find the time derivative in terms of time, we have to do a bit of manipulation. We have to either find an implicit derivative or we need to use chain rule. So kind of what we've done here is start off with a different equation, but you could have started with just your definition for v dot right here, just like this, and you could have done chain rule, and you could have said, okay, let's expand this, and we'll keep going d times dt of that equation. Sorry, we can write it as dv ds dt. So then if that was the case, we would need to know our change in position, our position function with respect to time. And we don't really have that. Sorry, we do have that in the equation. ds dt is just equal to v. ds dt is just our definition of our speed, right? So we end up with dv ds times v, which is the exact same thing we had over here.
Perfect. Thank you.
So either way you'd want to go about doing that, you could start from our equation like we did here, or you could have started from the definition of your speed, and you would end up at the same spot. So our final answer then, the magnitude of our acceleration is 40.8 meters squared. Okay, example 2. A train engine at point E, or we care about the part of the engine that's at point E, has a speed of 20 meters per second and an acceleration of 14 meters per second squared, acting in the direction shown. So that's 75 degrees inward towards the radius of curvature from the direction of motion. Determine the rate of increase in the train's speed and the radius of curvature of the path. So what are we going to do here? So this question seems kind of backwards. We're not given path functions and asked to find accelerations. We kind of have to work backward and find information about our path. So let's just write down some equations that we're probably going to have to use and see where that takes us. So let's start off with saying, let's just look at acceleration. And if we write down the equations for our components, we look at the tangential component first. That's going to be essentially the component in this direction. So our tangential acceleration is going to be the component of our total acceleration, 14 meters per second squared, acting tangent to the path. So we can write that as 14 times the cosine of that angle, 75, which would be equal to 3.623 meters per second squared. And then we know this is also equal to v dot. If we write down the equation for our normal component, that's equal to the component of our acceleration in this direction, which is equal to 13.52 meters per second squared. And this is equal to our speed squared divided by rho. So it's asking determine the rate of increase of the train's speed and the radius of curvature of the path P. So we've basically answered our first question with the actual first equation. The rate of change of the speed is the tangential component of acceleration. So we can just write down the first answer. V dot is equal to AT, which is equal to 3.623 meters per second squared. So that's our first answer. And then the radius of the curvature of the path. Well, we know our speed at that instant is 20 meters per second. We know the normal component of acceleration. So using the expression for normal component of acceleration, we can solve for rho. And we can write rho is equal to our speed squared divided by an. Our speed is 20. Our normal acceleration is 13.52. And so we should get a radius of curvature of 29.6 meters.